Hello, everybody. Thank you all for coming. It's been a while since we've done this sort of thing in person, and I'd forgotten how scary it is to stand up on here seeing so many people there. So, yeah, I'm more used to doing this in an empty room. So if any of you want to leave, now's your chance. So anyway, hello, my name is Matt, and I'm going to be talking about pattern matching in C#. We'll have a bit of an overview, have a look at it, see what it's about, see what's going on, and see if we like it or not. And just to clarify, we're talking about pattern matching here. We're not talking about design patterns, and we're not talking about pattern recognition and sort of regular expressions and that kind of thing. So we are talking instead about pattern matching. If you haven't come across it before, pattern matching is, well, funnily enough, there's no sort of authority to cite on what pattern matching actually is. You know, you can't go to Wikipedia and say, this is the definition of pattern matching. And so you kind of have all these languages that implement pattern matching, but not to a specific sort of spec. So they just implement the pattern of pattern matching, which is quite nice. I like that. But anyway, what pattern matching is, it's a means of testing a value to make sure that it matches a specific shape. And then it optionally extracts information from that. A specific shape is a kind of a weird sort of thing to say about a value, but what I mean there really is that it matches certain conditions and certain characteristics. And so these can be very sort of simple things, like a value is 42, or it be something a bit more complex, that it is a person object with a name, with a specific name, and an age which is greater than 18, and so on. But one of the key characteristics of pattern matching is the ability to not just match complex characteristics, but also to extract information and use that later. Before we dive into C#, though, let's have a look at what it looks like in some other languages there. Pattern matching is used all over the place, lots of different languages. It's been around for a very long time, longer even than me. And if you have a quick search on Wikipedia, one of the things that pops up is Snowball from the 1960s. I have no idea what Snowball is, but apparently it has pattern matching. So, well done, Snowball. It's also very popular in functional programming languages. I bet everybody's probably heard of it from functional languages such as F# and OCaml and Haskell and so on. But it's also used in various procedural languages as well. So Swift and Scala have both got it. Java is starting to get it. They are sort of following the C# route. It's looking very similar so far to what we've got in C#. Interestingly, talking of Java, Kotlin doesn't have it. And there are conversations about it, but right now there's no sort of real movement on that. Kotlin has something different, such as smart casts, which are testing an instance, testing a value is of a particular type, and then using it like that type. So I can say, if X is a person, then use X like it's a person. So you've got some sort of flow typing there, which is good. And Kotlin's also got a very powerful sort of when expression, which is kind of gets rid of some of the need then to have some pattern matching features in there. But even crazier, even C++ is getting it too. There's a proposal being worked on and going through there. So has anyone tried F# and pattern matching F#? A couple? Right, I'm going to scare you with some F# now then. This is quite an interesting, quite a thorough example. I'm not going to dive too much deeply into it, but to quickly talk you through it, on the left there we've got a type, and this is a shape, and this is a discriminated union. If you're not familiar with F#, that's essentially like an enum with data. So we've got a shape here which can either be a rectangle or an ellipse. If it's a rectangle, it's got a position and a size, and if it's an ellipse, it's got a position and then a min and max radius. Or it could also be a composed shape, which is a shape made up of two other shapes. So it could be a shape with two rectangles. On the right, we've got a function which is going to calculate the area of our shape. And we've got this match keyword here, which is kind of like the switch keyword in C#. We're going to match on shape, but it's going to do pattern matching for us. And we've got several actual patterns in there. First one is rectangle, and I'm going to ignore I've got an underscore there to ignore the position, and I've got the width and height there. I'm decomposing the size into width and height. I can very quickly then multiply them together, get the area. Ellipse is very similar too. I match on ellipse, I ignore the position, I've got my min and max radiuses, and I can work with that. Things get a bit more fun with composed. If we jump down to the bottom one, we've got a composed of two shapes. I recursively call the area function there to get the area of those two shapes and add them together. And I do some hand waving to get rid of some intersecting area there as well. Where things get more powerful is the first composed option there. And we have to order them like this as well because patterns are evaluated in order. But this first composed item here is going to match two rectangles. And it's got a condition there to say when one rectangle is a nested rectangle. If one rectangle lives completely inside another rectangle, then I can optimize this and just return the width and height of the owning rectangle there. So it allows me to sort of match on this shape here. I've got a composed shape, which is made up of two rectangles, one which lives inside the other. I can very concisely write that down. But it's not just about sort of matching a pattern to do a thing like that. Something like Haskell can take this and use pattern matching when declaring functions as well. So if we're in Haskell, we can actually declare a factorial function, and we can declare it with two actual method instances. We have one where the parameter is 0, and we can just return 1. And then we have another method declaration which has a pattern of n. And n is just going to match anything there, and it's going to bind the value that we have passed in there to the name n, and we can use that n inside the definition of the method itself there. So it's very interesting. You can do pattern matching for different things here. You can use it for working with data like that, or actually choosing which method to call. Now you can relax. We're not going to do any more functional languages. We're going to get back to some C# here. And what do patterns look like in C#? That's one. Oh, okay. How about that one? No, this one? All right, so that's kind of the wrong question to ask, really. So we're not really going to say what are patterns here. The better thing to do is back up a little bit first and say, where can we use patterns? Because we can't just sort of have a pattern there. We need to be able to use them. And in C#, we've got 3 places we can use it. We can use it in an is expression, which we should all probably be familiar with. If statement's there. If x is person, we're testing to see whether it is a person. And if it is, then we're going to assign that value to the person variable, which is going to be of type person. We can also use it in the switch statement case labels. So exactly the same thing there. Switching on x, case person. So if it's a type person, we can assign it to the person variable and do something. We can also use it in in a switch expression. Has anyone come across a switch expression? This was in C#8. Right, a few of you. This is a new bit of syntax there for using using switches as an expression rather than as a statement. And as a bit of a reminder here, then an expression is something that has a value, while a statement doesn't. So an expression is going to be anything. It could be like a method call, which returns you back a value. You know, get age is going to return me back a value of integer. Whereas a statement doesn't have any value there. So an if is a statement because you can't assign it to anything. It's completely by itself. So with our switch expression there, we can actually see that it's being called x. It's in an infix fashion there. So we've got the expression we're trying to work with, x, and switch, and then we can do some work with that. And then the return value of that is being assigned to something. And if we look at the types of these different expressions, an is expression is a Boolean, and that's why we tend to use them in if statements there. So if x is person, true or false, and we use it there. Switch statement, that's a statement. It doesn't have a value, so there's no type. And the switch expression, I'm assigning that to a variable y, and the return, the type of variable y is the return type of the arms that are in the switch there. Here I'm calling a method called getValue, and that's going to return me back an int in this case, and so the type of my switch expression is an int. And speaking of history there, switch expressions there, C#8, pattern matching has been around with us for a little while now, actually. I was a bit surprised when I was looking at this. I kind of was under the impression that pattern matching was a C#10 thing. Turns out it's not. It started in C#7. We've got a few things in there. Not terribly exciting for that, but then things really got going with C#8 and 9, and we've got some more interesting features in C#8 and 9, and C#10 is actually just a little tweak more than anything. Right, patterns. Let's have a better look at some patterns here. I'm going to start with a couple of things that you're probably going to find familiar. This one is a type pattern. It was introduced in C#9, but it looks very familiar. If X is person, that's just going to be checking the type of X to see whether it is a person. Excuse me. And it's going to check to see whether X at runtime is a person, derives from person, implements an interface, which might be called person, and it'll also do things like implicit conversions and boxing and so on. Now, this does look a little bit familiar. This has been around since C#1, but in C#9, they introduced a type pattern, which effectively changes how the is operator works. And so instead of it being this type, an actual type expression and a type check, it is now a pattern check. And X is person is now a type pattern. So it kind of retcons this and retroactively makes that into a pattern statement. But this particular syntax only tests for a type. It requires casting before use. And so for that, we need to use a declaration pattern. And again, I'm sure people are very familiar with this one. If X is person, then assign it to a new variable called person. This tests the runtime type again. If it's the value is null, then it doesn't match. And so we would get false in this. You wouldn't go into the if statement. And one of the interesting things with this is that it controls the scope of the variable assignment. So the person variable is still defined outside of the if statement. However, it's only assigned inside the if statement if it's true. So if X is person is true, then person only has a value once you're inside the if block. The other thing to point out here as well is it's got a really ugly syntax for negation. If you want to say if it's not a person, you've got to do this not brackets and all that kind of stuff. And we got some dots on the is there to kind of tell us that there's a better way of doing it now, which is nice. We'll get onto that. Another nice simple one we've got here is a constant pattern. You can just check to see whether a variable is a particular constant. So if I is 42, it's an integer, it's got the value 42. If S is a string and says hello world, we're good. And so those are very simple equality checks. And it's not, you can only really work with constants here. So you can't compare against a variable, you can only compare against a constant, but you can compare against other constants defined in fields. So you can use int.maxValue, or you can use my max count, or whatever. We can also use null here as well. So we've got yet another way of checking for null. I think C# is probably about 10 different ways of checking for null or not null. So it's take your pick. And of course, I'm using is as an example here. Same with the type tests we've got before as well. But you can also use them in switch statements and switch expressions. So you can have a switch statement with these constants as part of the case labels. Or you can have them in the expression there, and it's going to return back a specific value based on the match on the constant. You might notice that the switch statement has got an underscore as the last item. This is a discard pattern, and this is going to match anything and then throw it away. So it ignores it. This is because the switch expression does not have a default case like the switch statement does. And so you've got to have another pattern there which is going to match anything and finish up and make sure that your switch expression is exhaustive. It matches everything. If you don't have something being matched there, you could end up with an expression that doesn't return a value. And then that's not an expression, then it's all weird. And we don't want weird, I don't think. The other important point with the discard pattern, though, is it means that order is important here. So if we've got a switch expression, the order in which we evaluate those patterns is important. If I put that discard right at the top, it's going to immediately match, and it's not going to check any of the other patterns there either. And so order is now important inside a switch statement and also inside a switch case. Always get it the wrong way around. It's important inside a switch expression, as shown here, but it's also important inside a switch statement in the case labels as well. Whereas previously, switch statements, order wasn't important. So the underscore there as well is going to be familiar from things like lambda parameters and deconstructing variables where you might want to ignore the value. It's the same sort of thing. We're using it again. So you're looking at this now, and it's like, great, we can compare against equality against a constant. I can check something is a type or an empty value or anything. Is that really anything better than an if? And right now, I would say no. We're probably not there or anything. So we probably want to have a look at something a little more interesting and start to use some more complex patterns. The first one we're going to look at, though, is a property pattern. This was introduced in C#8. This is where things started to get a bit more interesting. And this can match a field or property of an object. And we can optionally match the type as well. So here I'm saying, if O is a person, then match the name property and see if the name property is mat. If so, store that in the person variable. We can optionally match the type. If O is already a person, that type there would be unnecessary. And we also don't need to assign it to a type there as well. So we can just have it where it's just matching the properties, or we can have it doing everything there. We can also match one or more properties or fields there. So we can have something which is a bit more complex. So I could match the first name is Matt, second name is Ellis, and so on. What's interesting here is yet another way to check null. Well, not null. If you have no properties listed in your property pattern there, then it's just going to match anything that is not null. So we have yet another way of saying, is this value not null? However, that's getting a bit funky, that syntax there, so I don't like it. We've also got a var pattern. This matches anything and assigns it to a new variable, which is kind of, frankly, a little bit weird. This is always going to match. If x is var y, yes, it is. And now we've got y. And it's like, OK, thanks, C#. Why? And the reason for this is that it's actually useful for working inside an expression. So we can have something, a much longer expression, and pulling value out from, say, the results of a method call, and then using that to be able to test the results there. So if I've got, get value, store that into a temporary variable, I can say is valid value and is greater than anything value and is this, then do something. So it's useful to be able to pull that out. It can be used to match multiple values as well. So I could use it to match x and y, so it can deconstruct stuff for me. And we've also got a discard case here as well. So var underscore will match anything and ignore it, which is, I still don't really know a use case for that one, to be perfectly honest. But you can match anything and then throw it away. But where this is really useful is with recursive patterns. And recursive patterns is where we're really starting to put things together and get some power out of this. And when we're talking about the property pattern, I kind of just didn't really explain this one properly. I said that we're going to match the name, what's the name property to see whether it's equal to Matt or not. But the way you do that is fairly obvious. You do it with a pattern. And here, this is just a constant pattern. So I'm using the constant pattern Matt to match it against my actual property. You can get a bit more interesting and do things a little more deeper here and have a proper sort of recursive pattern. And you can match that a property has then itself got complex properties. So let's say our name property here is actually a complex type. It's got two separate fields, two separate properties for first name and surname. And here I can match that, and I can actually now say that my person has a name property, and that name property has a first name on it, and that first name has a constant pattern, which is Matt. So I'm starting to sort of nest these here. But you can now see that we're doing something a bit more powerful, and we're describing a much more complex shape that we want to match. But that is a syntax that only a mother can love, really, isn't it? It's what it is. There's not a huge amount we can do with it. C#10, the little tweak that it did, introduced some sort of extended property syntax there, so we can do name.first, which makes it a little cleaner. However, these can still get a bit clunky and a bit awkward. But it's what we've got. Now, that var pattern, this is where things start to get, again, more interesting, because we can actually use that as one of our recursive patterns. And where we've got matching a constant pattern on the first name, I've now got a var pattern on the second name. So what this is going to do is it's going to say, get me any person that has Matt as the first name, save that as the variable person, but we're using the var pattern to capture the surname. So inside my if statement, I can now use the surname. Does that make sense? cool. I just got to scan the whole room to see. So you can start to do more fun things with this now. So it's starting to get more powerful. So I can match something with a more complex shape, and I can pull data out of that shape. Inside the nested pieces, I can pull data out and use that somewhere else. So now we're starting to see, well, this isn't just simple if statements. Doing this with an if statement, you can't. You're going to have nested things going on here. You're going to have check to see if it's a person, check with the first name of Matt, then assign that to a new variable, and then check to see what we want to do with that. All right, a couple more patterns to rattle through, and then we'll have a look at something a bit more fun. How are we doing for time? Because we can work with sort of recursive patterns, patterns that use patterns, then we've got the scope to be able to do something a little more interesting, and we can have logical patterns. So and, or, and not. And we can have a not pattern, which says this pattern does not match, and this is a nice way of doing not null or is not person. So remember when we had our type pattern there, we had exclamation mark brackets, X is person, and it's kind of ugly. Well, now I can just do X is not person, and it's much cleaner, much nicer, and it actually reads sensibly as well. We can apply that to our constant pattern, and we've got another way of checking for null or not null there, and we can evaluate that. And we've got the and or in there as well, so I can check on multiple things. I can check to see if my integer value there, if it's a value of 42 or it's a value of 100, and act appropriately. Now this is, I could do this with I equals 42 or I equals 100, but the benefit of doing it with a pattern like this is I only need to do the expression once. So if I was a calculation, if I was doing get expensive calculation equals 42, I'd either have to introduce a temporary variable outside of my if, well, that's all I can do, really. Whereas what I can do here is I can use the expression just once and then apply multiple patterns to that one value. And then relational patterns is another one as well, and these are quite similar sort of idea. We check to see whether the value is greater than, less than, greater than or equal to, less than or equal to a specific pattern. Sorry, not a specific pattern, to a specific constant. So these only work with constant values. So that's probably good. It's great for this particular example. It's great for various other examples we can come up with. It's checking against a constant value. It's checking against a char literal here to see whether it's going to be a character, a letter-based character rather than anything else. Obviously, don't use this in production code because there are more letters out there. And it's great for checking ranges and working with the logical patterns, the and or and not, and so on. But there are probably times when you want to be able to sort of configure what those ranges are. So, for example, if we had a relational pattern which checked whether something was within a particular tolerance, and we wanted to be able to configure that tolerance, we can't do that with a pattern because the pattern only works with constants. So we would have to then sort of break out into more traditional if statements. And again here with the very similar to the logical patterns there, we only need to create the value once and we get to reuse it. But it can look a little bit weird when we've just suddenly got these relational operators sort of standing by themselves. Last pattern to look at, but this one's much more fun. Positional pattern, it matches on deconstructed values. And so here, again, if we're talking about a name which is a bit more of a complex type, which has got a first name and a surname, I want to be able to match on those, and I can do that with this syntax here. So it looks like a type test again, but then I'm using the brackets to specify my positional parameters. And what this will do under the covers is to invoke the deconstruct method and matches the patterns on those results. So I've got recursive patterns inside the brackets there. So that Matt and the Ellis there, those are both constant patterns which are matching recursively on the deconstructed values. This one took me a little while to get my head around. This was something which I didn't like very much. It was initially something which made me not like patterns very much, that and the syntax of property patterns. Because this looks like a method call. And I couldn't figure out, well, is it a method call? But if it's a method call, that looks like a constructor. So is that a call to the constructor or something? And the answer is no, it's not. And that's why I've put a space in between the name there and the brackets. It's a type check followed by then positional parameters, deconstructing and getting these values out. One thing that is quite nice with this syntax, however, is that at the same time, it does look a little bit like a constructor. So you're kind of saying, give me a name which is, looks like this. And so you can actually sort of see it's almost the opposite of a constructor. It's describing, again, the shape of the name that I want, which is quite a nicer way of remembering what this means here. But there's no method calls going on. There's no new instances being created, and so on. You've got a couple more things you can do with this particular pattern. You can add on property patterns at the end of it. You can assign it to a variable, and it's fun. But let's back up a little bit again. Deconstruction. Has everybody used deconstruction with like tuples and things like that? Right. A few of you. That's cool. Let's cover a few things there. So tuples. We can use tuples here, and we can deconstruct them. So a tuple is a lightweight instance of a type called value tuple. It's a struct. I forget which version of C# it was brought in to be perfectly honest. But we've got language syntax to be able to do it. Brackets 1, 2, 3. That will create us a new instance of a tuple. And we can assign that to t. T is now of type value tuple, which is a generic type, in this case with 3 values. We also have support in the language for deconstruction. And I can use this bracket syntax again with a var keyword to deconstruct that into new variables. So I've got a variable A and a variable C, and they match the first and third items within this tuple here. Excuse me. The second item is an underscore, and again, we've seen that before. That's one of our discard kind of things. Discard, 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 right. Basically, that's just saying ignore it. I don't care about the second item here. I just want to use the first one and the third one. And I've deconstructed it. I've put those values into the variables A and variable C. Now, again, with this syntax, with the brackets on the left-hand side of the var, it kind of does look like a tuple again, but it's not. This is deconstruction. So what I end up with is an A and a C as separate variables. So there's no new instance of a tuple being created here. It's just about deconstructing. Yeah. I can do the same with user types as well. So if I've got my name type, which I'm creating there, the new instance of that, passing values into the constructor, I can then use the deconstruct method to pull those out. So it's the same syntax with the var brackets, first name and surname, 2 new variables, 1 first name, 1 surname, and that will be the deconstructed value of my name. And the compiler does this by calling the deconstruct method. It's got out variables, out parameters, and those are just assigned and populated. So again, when the compiler is done with this, we end up with 2 variables, which have got the first name and surname. So if we jump back to our positional parameter here, a positional pattern, what we can see is this is going to invoke the deconstruct method, and it matches then those patterns on those results. And so that's calling the same deconstruct method which I just had, and it's going to use the constant pattern on the variables that it's pulled out of that. But speaking of tuples and brackets and all that kind of stuff, we can match on multiple values as well. So this makes us, gives us even more power behind our pattern matching. Here we can actually look at multiple values going in to see what's going on there. So here I'm looking at 2 values, I and O, an integer and an object. I'm making sure that the value of I is 42, and also that my object is a person, name of Matt, and age is slightly over 21. And again, we've got the brackets going around the value at the start. That's just syntax. It's not creating a new tuple here, so there's no allocation going on there. Yeah, and this is a great way of doing complex conditions between sort of unrelated values there. So in this particular example with an is perhaps not terribly useful, but it's more useful when you're using a switch statement, and you can then look at a whole load of things. So the I there could be a value for, I don't know, employee status, and it could then have a check on all the different employee statuses you could have, and then the person on the other side. Right, so that's a quick run through all the different patterns we've got that are in there, and what's kind of missing there. As I said, with a constant pattern, we can do a check to see whether something is a constant value. Our relational patterns use that, then they compare against constant values, but we can't compare against a variable itself. This is the case across a number of different languages. F# is the same, I believe, so you can't compare a relational value against a variable, only against constants. But I think C++ is looking to do just that, and I think that's actually causing them some headaches, because then you don't quite know what you're parsing and quite know what the pattern looks like. But that's okay, you can still just extract it to a variable and compare with a traditional if test. The other thing that's missing is if we wanted to look at the property parameter, the property pattern, we can only really look at sort of simple properties in a way, or complex properties, until you get down to a simple property. You can't look at lists. You can't look at the third item in this list, or you can't say, does this list have 4 items there? Actually, you can, because you can look at the length property to say that the length is 4, but then you can't look at the values within that list. Right, so how do patterns work? I mean, the kind of syntax which we've seen so far has been very, very declarative. They're not executable code there. This is just describing a shape. It's looking declarative. So how does all of this work? How does it all work under the hood and everything? And basically, it's compiler magic. The compiler just rewrites everything. It's a mechanical transformation to change it, but it's not obvious what's going on under the covers there. So if you're familiar with iterators, the yield return statements, there's a fairly mechanical transformation that's happening under the covers there to convert into a state machine, and which can sort of save the current states and then jump straight back in and return the next item. There's a similar but more complex transformation going on with async await. Link is a very simple transformation into method calls, and so those kind of make a little bit more mental sense to me, fit my mental model of what's going on with C#. But with patterns, it's a little less obvious. And so we can have a quick look at some of these things. So I've got an example here, which is off the .NET sites. There is a set of .NET samples as part of all the C# stuff, which gives you a nice tutorial really for working through pattern matching, and how to use pattern matching, how to evolve a bit of code into using something which is based on patterns. And what we can do is we can have a look at some of these kinds of things, see some examples of where we might want to use it, and then see how the compiler actually, what it looks like under the covers. So I'm going to jump to a simple one first. Hang on, I've lost my... One sec, sorry, I've lost my... that one, that was what I wanted, yes. So the isLetter example there, so if we... Yes, the problem is I've lost the source code for that one. That was what I was looking for. The original, if we remember the isLetter check we had a simple return statement. I'll just grab it back off here. There's a couple up there. I've passed it. That one, that's right. Given a pattern like this, we've got a method there, isLetter, It's an expression-bodied item there. We're just going to return back the result of this is expression as a pattern. And we're doing a relational thing. We've got that it's between A and Z lowercase, or it's between A and Z uppercase. We can then sort of see what's going on and how that's sort of decompiles to. And basically, it doesn't decompile into perfectly, or into the same C# that you would write yourself. So the code that the compiler generates is a little different to the code that you would. And so when the decompiler sees it, it doesn't recognize a normal set of if statements. And so we end up with gotos and things like that. But we've got a similar sort of flow going on here. Again, the order of the flow is important. First checks to see whether the value is greater than A. If it is, it's then sort of checks to see whether it is greater than Z lowercase. And if so, we jump to label 4, sorry. And we basically then return false. So that's failed. So it's if it's less than Z, so if it's greater than A and less than Z, we end up at this state here with setting a flag, jumping to label 5, which is exit. So again, this isn't necessarily the code you'd write, and looking at it, it takes a minute to get your head around what's going on here. But it is still just sort of simple if statements. Well, when I say simple, I mean, they're nested, they're complex. The pattern we wrote was shorter and simpler. You know, this one particularly here now, that's a nice, much more easier pattern that we would recognize. Sorry, not pattern. An easier if statement that we would recognize and that we would write ourselves, and it would show us what we've got. We can also have a look at our property patterns. Yeah, I got the code for that one. And again, this is going to be a very similar sort of example as was shown in the slides. Can everyone see the font size big enough, by the way? Everyone happy? Cool. Yep, so we've got two patterns going on. Here we've got a simple one at the top. We'll look at that one first. If O is person, and then check the property simple name is Matt. My definitions are down here. I got person with a string property, simple name, and a name property, complex name, and then name one is just a type. So if we look at the simple property pattern first, if I swap back into the decompiler, yeah, decompile code, there you go, that's actually quite nice. That one's decompiled quite nicely there. We've got a type pattern. It recognizes it's looking for a type, assigns it to a variable, and then just checks that the variable is the constant that we've got there. So that one's nice. I can break that one down. That one's good. If we look at a more complex pattern we've got here, which is going to be checking for a first name of Matt, and then saying, get me out the surname. I don't care what the surname is, just get it because I want to use it later because I'm going to write it out. If we look at that, what that compiles down to, we've got something here. And again, we've got gotos, because it's not the normal style of code that you would write, that the compiler would generate. And so the decompiler doesn't recognize it to be able to put it back into if statements. And so the first thing we do is we check that it's not null, because we've got lots of different ways of checking that it's not null. Then we pull out the complex name, we check that that's not null, and then we just check to see whether the first name is Matt. It is, and so we populate our variable, which we defined at the top here. I've got no idea what num equals 1 is for. Oh yeah, so that's the if statement. It basically says it's true that the pattern matched. Then we go to our label. If it didn't match, don't do anything. And if it did match, then we can write out our surname. So you can see that this is complex compared to the pattern that we wrote. The pattern is simpler. We can do a simpler check on several different things without having to jump through a bunch of nested if statements. Let's have a quick look at the tuples class. Does anyone have any questions just yet? Yes?
The null checks, are they done automatically for us in patterns?
So the question is whether the null checks are done automatically, and the answer is yes. So as part of a type check, it only matches if the value is not null. So if I've got if x is person, that only matches if x is not null. And if if I have a type check as part of my property pattern there, that is also going to make sure that the value is not null. So here, the value matches the type and is not null. So if I passed in null, if I called simple property pattern null, then this pattern would not match, and the null check does that for me. If I pass in a string instead of a person, that type check finds that, and it doesn't match in that case, even though the value is not null. Is that happy? Cool. Anybody else? Yes?
I mean, early days they said we shouldn't use ternary operator because by the multi-statements, but now we're going exceeding that, writing so much big logic in one line.
Yes. So, yeah, absolutely. So the comments about the ternary operator. So I haven't mentioned that at all yet. So I mentioned that the if statement, the ifs are statements, and ifs do not have a value. But if you want to do something similar to an if-else statement, you can use the ternary operator there. That's where can I? That would be something like var x equals o equals to null, question mark. Hello, colon. Well, so that would be the ternary operator in action. Okay. Is that, oh, have I got nullability on? There we go. Yeah, fine. See the C# nullability. So we can use the ternary operator to give us an expression there. So that's one way of sort of reducing some of the complexity which we can have with nested if statements and things like that. But pattern matching takes that further. Pattern matching sort of extends all of that, gives us a whole, well, it's a whole new language, a whole new set of syntax for describing the conditions that we want to meet there. So with the ternary operator, we've got our resulting values here, but the condition is still just that part there. Whereas with a pattern, this part is my condition, and there's a lot of condition going on there. To try and put that into a ternary operator would give us an equally complex condition at that side. Tuples. So the so one of the other things that confused me with patterns was working with tuples and deconstruction and stuff like that. Because you've got the bracket syntax, the positional parameters, the tuples, the deconstruction, it all uses these brackets sort of syntax there. It all looks very similar, and I don't know, well, when is it a tuple? When is it deconstruction? When is it matching on multiple values and things like that? So we can take a look at how that works here. I've got a struct point with an x and y. I can construct it here, passing that in and setting it up. Fun syntax going on there. There's like an expression-bodied thing to assign two things, thanks to brackets and deconstruction, just to confuse things even further. And then we've got a deconstruct method with two out parameters, and again, it's just assigning them at the same time to the x and y properties there. So I mean, that is the same as writing x equals x, y equals y. It's the same thing. So we can use that with a deconstruct situation here. So here we are deconstructing our point into x and y, and that's actually creating two new variables, x and y. That's not creating a tuple, even though that bracket syntax perhaps looks like it is. So that will deconstruct, and then I'm just using the two variables to work on as a switch statement there. And here I can match both values, 0, 0, I'm at the origin. I'm either all the way on the x-axis or all the way on the y-axis, or I can use my discard to match anything. And if we quickly look at the decompiling of that, in fact, the decompiler is smart enough not to call the deconstruct method there, but to give it to us in nice C# syntax. Let me see. This is one which might, if it wants to actually do anything. Oh, there you go. Okay, how's that? So this is decompiling to an older version of C#, which doesn't understand about the deconstructing syntax there. But you can see I've got my point value. I call the deconstruct method, and it creates two new variables for me there. So we're actually not creating a tuple, we're just pulling it out into variables. And then the way that the riders decompiler here has interpreted this is as a switch, and it switches on the first value, the x, and if it's 0, it then sort of checks the y value. 0, 0 gives me the origin, 0, 1 gives me my y-axis. If it's 1, it then checks the other value to match against that, and otherwise I've got a default case, and we're all done. So again, sort of a fairly complex bit of code being written there, which is much more concise and perhaps readable there, because we've actually got like a table of the values that we want here. So this is now where pattern matching starts to show some use, because we can make it more readable, and we can actually just show a table of the values that we're going to be using here. Okay, the question was, do you have to deconstruct it? And the answer is no. I wanted to show the difference here, really, because the next one here, I am creating a tuple from that. Well, in fact, I think I could probably just do that, and that will work as well. So the switch expression will deconstruct it itself as well. So I didn't have to deconstruct it myself, but the switch will do it too. We have a sort of similar pattern going on here, where I'm actually creating a new tuple, and this is going to be a new allocation, a value type here of the tuple, and then I can match that on the switch, and it pretty much gives us basically the same. Let's have a quick look at some more examples of when you would like to use of pattern matching and so on. So the example that's used in this tutorial is of a toll, and it depends on what type of vehicle goes across, how many passengers there are, and so on. There's various different conditions for doing it. And what we can do here is we can, first of all, switch on the vehicle itself, what kind of vehicle it is. So here we're saying, well, okay, it's a car. We'll do something based on that. Otherwise, it's a taxi. Otherwise, it's a bus, or it's a delivery truck. And then find last two patterns. Well, it's something, but I don't know what it is. So let's throw an argument saying it's an argument exception, saying that it's an unknown type of vehicle. Or it's null. Somebody's passed me null. That's bad. I don't know what to do. I'm going to throw an argument null exception. But we can do lots of different things with our particular switch statements here as well. So if it's a car, well, then I can do a nested switch to say, well, how many passengers are there? If there's 0 passengers, how do you do that with a car? Okay, if you have a self-driving car, then it will charge you more. If there's one, presumably passengers on top of drivers, then it gives you your total of $2, pounds, whatever. If there's 2, a different deduction, and any more than that, you get a maximum deduction. And so it's nice there. Similar sort of thing for taxis and fares. You can decide what you want to do based on something within the taxi. You can do more fun things with, if there's a bus there, we can have a when expression to say, well, if it's a bus with this information, do that kind of stuff. And we've also got a similar sort of when clause with the delivery truck, but we're also getting a highlighter there, so we can say we can merge it into a pattern, and we can pull that out now, and we've got a slightly more complex pattern, which says it's a delivery truck, and check to see whether the gross weight class property is greater than 5,000 things, and then give it a different value from that. The other example, which is fun, is this one, which is the peak time premium. So if you've got your toll, you've also got a peak time premium, which is added on top, or as a multiplier, I think it is. And there's a whole set of rules that are going on about that. And here we are trying to figure that one out, and we are matching on several different things. Is it a weekday, or is it the weekend? What time it is, morning, daytime, evening, and overnight, because it's going to change from that, and whether you're inbound or outbound. And here you can see you've got a full table of the states there. So this is great. There's a way of being able to list your entire state table there and work with it. And this is useful for making sure you've got all those things going on. But we can see that there's, we can see that there's some redundancy. So, for example, here we've got, well, it's a weekday, it's daytime, and I don't care whether it's true. Sorry, the inbound true and false are both giving us a premium of 1.5. We could simplify that. We could use the underscore discard pattern there, and we can then match both at the same time. We get a warning to say it's already been handled, so we can delete that, and then we can actually simplify this pattern down using discards to something that looks a little bit more like this, which is a lot more readable. And it's a lot more expressive, and it gives us a lot of power there as well. So we can say, yes, it's a weekday, and whether if it's overnight, give it this one. If it's daytime, do it that. If it's the morning or evening rush, depends on your direction of traffic. And everything else is just the normal sort of premium. And to put that into an if statement, you end up with something like this, which is, less readable. And I think, you could probably clean it up with, using the ternary operators going on there as well, and you could probably get rid of a few things to clean it up and that. But even so, that's is not quite as concise and as readable as this sort of state pattern, state table that we've got going on here. Okay, let's finish off. What a pattern is good for, we've had a look at a few examples there. The states table there is really useful. It's great for reducing nested if statements because you can declaratively describe the shape of the thing you're looking for rather than sort of procedurally checking for it. You can describe things as a state table and check multiple values all at the same time. And the other thing, excuse me, the other thing which is really useful is being able to pull the data out of a complex condition, especially sort of several layers deep if you're using a nested property pattern. There are several sort of canonical examples. If you kind of look at this, the sort of pattern matching sort of tutorials for more functional languages, you're going to get things like, working with tree structures. And so, for example, if we've got a node here which has got several subtypes of describing an expression, an addition, multiplication, negation, then the traditional way of doing that in a sort of procedural language would be to use a visitor pattern and be able to sort of walk through all those nodes at once. Here you can just do it as a pattern. We can we can match our node there. If it's a constant, pull out the value itself. If it's a negation, well, make it to negative and evaluate the child node that's available there. If it's an addition, evaluate the two items on the left and the right. If it's a multiplication, just multiply them. Otherwise, it's a node which we don't know. But you can very concisely evaluate an expression just based on that there. So it's matching a tree structure. Does that one kind of make sense? Okay, cool. How about this one? So I lied about the functional programming. There's one last one. This is Wikipedia being pure Wikipedia. This is great. It's like search for pattern matching on Wikipedia, and it says, look, here's a fantastic example. And it looks terrifying, I have to say, but it's actually really smart. This is for rebalancing a red-black tree. Red-black tree is some kind of binary search tree. And so basically you've got, each node has got a color to say what state it's at. It's got a left tree, a right tree, and a value. And you want to rebalance it to make sure that your tree is not too lopsided. And what this does is it basically has 4 conditions at the top there, which matches unbalanced trees. And they can be nested, so you've got trees within trees. And you've got patterns which describe variables to pull them out. And then at the end there, it just describes a brand new tree, which is balanced. And that's really smart. It's hard to unpick because there's lots of commas and brackets going on in the different places. But you've got 4 conditions matching the unbalanced tree and pulling the data out, and then you just create one balanced tree to do it. Doing that procedurally with if statements would be a lot more code than that. It might possibly be slightly more easy to understand, but we'll skip that. So, to sum up, pattern matching tests that the value is of a specific shape, that it has certain characteristics. More importantly, you can extract the information out from within the test for later use, and you can combine all these patterns to make more and more sort of complex conditions to match your characteristics there. And this can help you to reduce your nested if statements, make everything a bit more declarative. With C# you use is to match a single pattern. This will give you back a Boolean true false. Otherwise you use a switch then to choose between different patterns to be able to perform an action. And so that brings me to the end of everything there. If you want to have a look at the tutorial, which I was showing some of the code for that, calculating the toll, it's a good tutorial which will walk you through sort of changing some code from a procedural way into a pattern matching way. The link's at the bottom there. Other than that, thank you all for coming and for joining me. And if you have any questions, please shout out. Yeah. Hello.
You said you specify the patterns, but if you don't know the type, say you have a method and you can send in a person, you can send in a customer, and the only thing you know that I want to know if this has a property called name, and I want to use that name. Can I do that? Say curly bracket, name, and a var, or do I have to specify a type? Okay, so that's a really good question. So if we were looking at a property pattern, I'm looking at things like the name being Matt, the surname, the age being over a certain thing there. And when I was doing it with a person type. And the question is, can we do that based on no type at all? Can we just say, well, I'm getting something in, I'm expecting to have a name, I'm expecting to have a surname, can we do the pattern on that? And the answer is no, because it's C#. C# is a strongly typed language, so you need to know what it is beforehand. If we are using the property pattern and we say person first and then put our properties there, forename, surname, age, then what we're doing is we're telling the compiler that this will be a person, or we hope it will be a person type. If we don't include that type there, then the type has to match whatever is in the object itself. So if I quickly find... Yeah, so if... Oh, it's an image, I can't do it. Yeah, here, for example, O can be an object, but then I'm telling the compiler, well, this object, I'm expecting it to be a person, and in that case, person has a name. We know that. The compiler knows that. But if O is already a person, that person type check there would be redundant. And then, again, the compiler still knows that it's a person, so it knows it's got a property of name. If O is an object, and I don't specify the type check, the compiler will go, I don't know what name is. You need to fix that, because it's C#, and C# is strongly typed. Anybody else?
So
yes.
In that case, you could put an or always customer. Or.
Yes, so the comment was you could use an or pattern there, and yes, you can use an or pattern. You'd probably use a switch statement in that kind of case there, because they're sort of starting to get into disparate things. But you could have if O is person, blah blah blah, or customer, blah blah blah, and that would work there. So you can do different checks there. But again, you still need to know what the target type is going to be, so the compiler can then know what the properties are and validate those and check those. Hello.
Hi. I get the feeling that it's possible to get high on these things, like we did with link, and like every loop became linked, and now every single if statement and everything will become. Is there anything you shouldn't do? Just stay away from.
I'm going to refer you back to the Wikipedia article. No, so that is a great comment. I mean, I love the way of getting high on this kind of thing. Yes, never get high on your own supply. Yes, it's very, very easy to overdo all of these kinds of things. We've done it with link. We've done it with so many other things. Pattern matching is probably going to be a very similar sort of thing. I don't know. It's the same argument that you have with link there. It's kind of you kind of have to use it to learn it, and you have to make the mistakes to realize when you've got it wrong and when you've overused it, to then roll it back and use it in the appropriate places. I think we will probably end up using pattern matching in lots of places. We're probably going to use it in smaller places where we would use normal if statements. So if I is greater than 10 and less than 3, rather than if I is greater than 10 and, I is less than 3. So we will write a pattern rather than just using the normal relational operators there. I think we'll do that kind of thing. I think to an extent where is it? The pain of this kind of syntax is probably going to stop us doing too crazy stuff with that. But then I think we'll have a lot of things. So again, that's going to be great because that's nice and concise and good. That's starting to not get great because that's just too much, and I kind of can't keep track of all of those conditions there to sort of say that, well, have I covered everything? Interestingly, I think the compiler will tell me. Yeah. So if I've missed something there, the compiler actually tells me that there's a value that hasn't been handled, which is useful. But also, if that had been, if that was a relational operator there, the compiler wouldn't necessarily tell me. But the compiler does a very good job of making sure that the switch is exhaustive. Okay. There we go. Have we got any time? I think that's it for time now, actually. So thank you all very much for coming. I'll be hanging around. If you have any more questions, please let me know. So thank you.